Welcome students. In this video, we are going to talk about elementary functions. So what do I mean by this? So if you recall, the only nice function which we talked about is this sort of function. F is from C to C given by fz equals to z power n, right? This we already did. This is for n in n. So basically z square, that sort of thing, or mod z power n, right? Again, n in n. This sort of function we already did, right? And of course, you can change n to minus n and all. So basically, an integer and all those things you can do, provided they are defined. So this sort of function we know now from the real part. We already know that there are other nice functions which we can talk about, such that the exponential and the sines and cosines. So here also we want to define similar sort of thing. Okay, so what is our aim in this video? The aim in this video is define exponential and trigonometric functions. Okay, now first of all, let's just see in real. So let me motivate you here. So let's say f is from R to R, right? R to R, and if you are looking at a function such that f prime of x is always equals to f of x. So essentially what you are saying is the derivative of f is always f of x itself, basically, such that f at the point 0, okay, so at the origin f takes 1. Now if I am asking you how many such functions are there, then you can show that there exists a unique f, right? This is a basic ODE, right? So there exists a unique f such that, so this is basically 1 is satisfied, right? 1 is satisfied. And what is that f? That f is given by f of x is exponential x. Yes. So now you see we are going to use this whole fact in our problem. So what we are going to do is we were defining function. Now what we will do is we will define. Okay, first of all, let me give you a small definition. So we were going to deal with something called an entire function. So this is an entire function. We'll call entire function. What is the entire function? The functions which are differentiable everywhere. Okay, entire functions. So functions that are differentiable, okay, at so this is differentiable at every z in C. Clear? So for every point in the complex plane, if some function is differentiable, we call that function as an entire function. Yes. Okay. And now with this definition in mind, so essentially if I'm asking you to give me an example of an entire function, you can now say that, of course, example, up till now the only example which you know is fz equals to z power n, right? N in n. We have defined it and showed that this is entire for all z in C. So basically this is entire. So basically differentiable for all z in C. Yeah. Okay. Now we want to find out more functions which are which may be entire. Yeah? Okay. So with that in mind, we start with defining something called the exponential. So now we define the exponential function. Okay. What is an exponential function? Okay. So you see, what do we know? We know that exponential x is already defined, right? So we are going to use that, yeah, and define something called e power z. Okay, so e power z will be defined as, so I want to define something like this. So basically what is e power z? See, e power z should be, this is motivation again, e to power z should be e power x plus iy, right? Okay, Now, if by some method, if we can write it like this, if we can do this, e power x times e power I y, if I can do this, you do realize that it should be, I mean, if it's a nice generalization, it's a proper generalization, we can somehow be able to do this. If you can do this, then this becomes e power x and cosine y plus I sine y. I sine y. It should do something like this. So e power z can be defined like this, but again, you have to make sense of all. So what we are going to do is we are going to take the motivation from here and define this. This is definition. This is definition. Definition. So whenever I am writing it, this symbol I am using, that means that this is a definition. Clear? Okay. So what are we going to define? How e power z, as it is defined as e power x times cosine y plus I sine y. Clear? And where are we getting it? We are getting it from this motivating idea. See here, e power x is well defined. See here, z is x plus iy, right? X and y are both real numbers. So e power x is well defined. Again, cosine y and sine y is also well defined. So basically, I'm putting all these things together and defining a new complex number, which you are saying, calling it to be e power z. That's what. Okay. Now, so with this in mind, you see, what we want to do is we want to explore some properties of this thing. If we define something like this to be an exponential function, we want to get out some properties of it. Okay. So first property is this. See, property. Properties. 1. E power z1 plus z2. z1 plus z2 is, let's see what happens. E power z1 plus z2 is nothing but e power x1 plus x2 plus I y1 plus y2, right? And then you can break it up. It becomes e power, so x1 plus x2 and then cosine y1 plus y2 plus I sine y1 plus y2. Okay, and then you can break this thing up. Then you can write it as e power x1 times e power x2. And you can break this thing up and you can show that this actually turns out to be cosine y1 plus I sine y1 and times cosine y2 plus I sine y2. I hope this is clear. Okay. If you put this and this together, that will give us e power z1 times e power z2. Please check this part. Check this. Yeah, this is true. This is true. Don't worry about it. No, don't worry means you have to check this part. Yeah, but this is true. Okay, just simple calculation and you are done. So now this is the first property which you actually assume that this is going to be true, right? So that's what this is. Yeah, and you see, let's say that property 2. If you take, if z equals to e to the power I y, then what happens is, you do realize this definition will give me e power z to be e power I y, right? And that will actually give us cosine y plus I sine y. This we already know. Sorry, we already know means we are suspecting because we have already learned in previous courses. So e power I y is cosine y plus I sine y, and this formula is a very important formula which we will call it as Euler formula. Euler formula. This you already know from your previous courses. So this is exactly how we are getting it. So we are defining the exponential likewise, and then from there, if you take z to the z as iy, then you get this particular formula. Yes. Okay. Now number 3. You see 3. See, if you are assuming if z, if you write it in a polar coordinate, right? R cosine theta plus I sine theta, if you write it like this, okay, then also basically I can write it like this, right? In that case, it is R. See, cosine theta plus I sine theta is e to your I theta, right? So you can write it as this. See, z is R e power I theta. Okay. Okay, we can write this. Okay. Now, and if you take y to be 2 pi, then e power z. So basically 2 pi I. 2 pi I. Yeah, this is going to be 1. This is okay? Yeah. So this is our general, I mean, some formulas are there. E to the power minus pi I is going to be, so similarly, you can also show that e to the power minus pi I is going to be minus 1. Yeah. So all of this is true. And also, if you take the modulus of this particular e power iy, if you take the modulus of this thing, this is nothing but cosine y plus I sine y. I sine y. Okay, that will be root over cosine square y plus sine square y, which is going to be 1. Clear? Okay, so those again, these are something which you already expect. Okay, right. So you see the pure part, so essentially the pure imaginary exponents of the exponential function, that has the absolute value 1 always. Yeah. So therefore, you see, mod e power x, if you do that, that is always going to be e power x. X is the real number. X is a real number. And if you're taking the modulus of exponential of x, that is going to be exponential of x. And that e power iy, that part, the cosine y plus sine y, that part is essentially nothing but 1, right? So if you therefore, that will imply that if you're taking mod e power z, that is always going to be 1. Okay, I hope this is clear. Because the other part, the modulus is always going to be 1. Sorry. This is exponential of x. Yes. And see, the exponential of x is never 0 for all x. Yeah. So mod exponential of z is never going to vanish. Yeah. So therefore, and moreover, you see, exponential of z can be written as exponential of x cosine y plus I exponential of x sine y. Now, do you think this is a entire function or not? It is going to be an entire function. How do you prove this is the entire function? So this is nothing but you can write it like u of xy plus I v of xy, right? Okay. So if u of xy is exponential of x cosine y and v of xy is exponential of x sine y, that will imply that ux equals to e power x cosine y, uy equals to minus exponential x sine y, vx is going to be exponential of x sine y, and vy is going to be exponential x cosine y, right? Now, of course, from here you see that this satisfies, so CR equation is satisfied, right? CR equation is satisfied. For what? Satisfied for all z in C. So basically for all x and y in R. And ux and So basically all the partial derivatives, and all partial derivatives of u and v are continuous. See here, these are all very nice functions. They are all continuous, right? So from our theorem which we did in the earlier video, we can say that will imply that exponential function z is differentiable for all z in c, which will imply exponential z is entire. Okay, it is entire. Entire means it is differentiable for all z in c. So you get another function which is again entire. Okay. Okay. So that is that. Now another small thing which I want to do is we want to find out what is the property. So this is another property of an exponential function. Okay, third property. Okay, the fourth property. Let's look at the fourth property. The fourth property is what is the argument of e power z. This is very, very important. Now we should know what is the argument of e power z. This is what is happening is e power z is exponential. So this is this, right? E power z is this particular thing. Exponential x cosine y plus I exponential x sine y. So what should be the argument? Of course, the argument should be y, and then you have plus minus the other part, right? The 2 pi part. So n 2 pi plus minus 2n 2 pi. 2n pi. So this is for n equals to 0, 1, 2. Okay. So that's your argument. I hope this is clear. Yes. Okay. So given this argument, we can actually say that the periodicity of exponential z. So what do I mean? Therefore, e power z plus 2 pi I. Yeah, this is the thing, but you can check that this is going to be e power z, right? Yeah, for all z in C. For all z in C. Yeah. What does this say? It says that the function has a periodicity of 2 pi. Therefore, and so exponential is periodic of period 2 pi. Yes, I hope this is clear. And you see, this is true all the values. So essentially they are also see periodic between 2 pi. So essentially what it is saying is this: every value of exponential z can be assumed in, so it also every value of exponential z can be will be achieved, not can be, will be achieved in minus pi y pi. Okay, and then so this between 2 pi. So basically, if you if you are looking for your argument, you start from minus pi. So okay, you start from here. So minus pi to pi. Between this particular thing, every other argument should be there. So minus pi to pi, right? Because that will give you 2 pi. So within 2 pi, everything is there because it is periodic. Yes. Okay. So this is a very important function, which is the exponential function. Now we'll define another function which is called the trigonometric function. So trigonometric function. Trigonometric function. Okay. So what are we looking at? We want to define cosine, sine, all these things. Yeah. Okay. So you see that e power iz, we already know, that e power iz is cosine z plus I sine z. Right? So, sorry, not z, x. This is x. cosine e power ix is cosine x plus I sin x. Okay. Okay. And therefore, and also e power minus ix, if we do, it is cosine x minus I sin x. Yes. So if we subtract those things together, therefore, what do we get is cosine x is equals to half e to the power ix plus e power minus ix. This we know from very beginning, right? The earlier courses. And sin x can be written as 1 by 2i e power ix minus e power minus ix. Okay, right. So this suggests that for z, which is x plus iy, we can define similar sort of thing. So what we are going to define, we will define cosine z. This is the definition. We will define cosine z as half of exponential iz plus exponential minus iz. Okay. And sin z to be 1 by 2i. Okay. Exponential iz minus exponential minus iz. Clear? So this is what we can define. And you can see that if you define similar sort of thing, you can actually show that you can also define, and hence tan z will be sin z by cosine z. This is not will be. We are defining it like this, yes. And we can define cot z to be cosine z by sin z. Okay. And of course, the secant of z is going to be 1 by cosine z. And the cosine of z is 1 by sine of z. Okay. So, these are the new functions which we came up with. Yeah, this is the new definition which we came up with. Now, with these functions, you see that you can, first property is this property. 1. See, all of this is entire. So basically, if you define not all of this, basically sine and cosine in the first of all this particular two. So sine z and cosine z are entire functions. Okay, why is this true? Can you tell me? Just think about it and tell me why is both of these functions entire. See, think of it like this. Exponential, so cosine is a combination of exponential iz and exponential minus iz and divided by 2. So exponential iz, that that is an exponential function that is always entire. And you are adding another entire function. So basically, the sum of two entire function is going to be entire. So it's quite easy, right? And then I'm dividing it by 2. 2 is also, you can think of it as basically a constant or as a constant function. So in that case, this is also entire. So cosine z is a combination of addition of two entire functions, which is again divided by 2. So cosine z is going to be entire, and similarly sin z is also going to be an entire function. So these are the entire function. Okay, right. And you can also do this. You see, check this part. So please check this. Check. Number 2. Now, this I am not showing you how, but you can show that the Euler function is also defined in the complex. So e power iz. You see, we know e power ix is cosine x plus I sin x, right? But here we can actually do e power iz is cosine z plus I sin z. Yeah, you can easily check this part, right? So please do that and see that this is also true. So basically, this is your Euler formula. Euler formula. Up till now, we knew that the Euler formula is defined for real numbers. Now we can show that the Euler formula is actually defined for the complex number also. Okay, right. So these are entire functions. Now, 3. I missed it, but since these are entire functions, what is the derivative of cosine z? If you just have to quickly do it, you can see that that's going to be minus sine z, because this is the exact definition which we use from real numbers. So it should actually follow the real path, right? And again, sine z prime, the derivative of it with respect to z is going to be cosine z, and then tan z prime is going to be secant square z. Yeah. Okay. We have more properties. Number 4. So you see cosine z, yeah, cosine z square, yeah, you can check this part that this. So okay, so let me do it this way. Yeah, cosine z. So check this. Cosine z is nothing but half of exponential I x plus iy plus exponential minus I x plus iy. Clear? So that will give me half exponential minus y cosine x plus I sine x. Okay, plus half exponential y cosine x minus I sine x. Okay, we can write it. Now, if we put everything together, you can show that this is nothing but half e power y plus e power minus y. Okay, and then you have cosine x minus half, minus I by 2, this is I by 2, e to the power y minus the power minus y, and then sine x. Clear? So you can write it like this. Now, from the real part, you already know that this is nothing but, if you remember, cosine hyperbolic y, right? So you can write it as half cosine hyperbolic y cosine x plus minus I sine x and sine hyperbolic y. Clear? Okay. If this is the case, you can actually show that the modulus of cosine z, yeah, this is also true, is nothing but cosine square x plus sine hyperbolic square y. Yeah, please check this part. Check this, huh? This is true. Okay. And similarly, you can also show that sine z, yeah, that can be written as sine x cosine hyperbolic y plus I cosine x sine hyperbolic y. Clear? Sine hyperbolic y. Yeah. So you can actually show this. Yeah, you can show this. Please show this thing. Yeah, is it true or not? This is actually true. Okay. Now, see. I let me write down what modulus of sine z is. Modulus of sine z in this case will be sine square x plus sine hyperbolic square y. Hyperbolic square y. Clear? Yes. So that is that. Now, one major property of this function, and you have to understand this thing, that what is the period of this thing. See, sine z, cosine z, it depends on, essentially, you look at this definition. Look at this definition. See, exponential is, the periodic of period 2 pi I, right? See, exponential, see, this is 2 pi periodic, right? Exponential is 2 pi periodic, right? And, sorry, I should write I, 2 pi I, 2 pi I periodic, right? See, 2 pi I, okay? So, exponential is 2 pi I periodic. So, you see, here, if you put all that exponential together, because of cosine and sine we are defining using exponential, you can actually show that the sine z, this is 5, sine z and cosine z are 2 pi periodic. 2 pi periodic. Okay, so please check this part. You can prove this here. Let me put a question also. Question: what is the period of tan z of tan z? Clear? Let me put this question. Right. Now, very important property is this. See, in real, we know that mod sine x is always going to be less than equal 1 for all x in R, right? This we already know. Okay, so does similar sort of definition works here? Let's see. See, sine x, if you look at the definition, so let's say this one definition, mod sine z. Now, from here, let's call it star. From star, mod sine z is nothing but sine square x plus sine hyperbolic square y. Okay. Now, this part is always bounded by 1, bounded, because x is real, right? Sine x is going to be bounded by 1. So, sine square x is always going to be bounded by 1. What about this one? You know that this is going to be unbounded. So, this is unbounded, bounded as y tends to infinity. Yeah, this you already know, right, from the real variable thing. Yeah, so the sine hyperbolic function, that is not going to be bounded, right? Okay, so therefore, let me put it this way. Therefore, sine z is not a bounded function. Okay, it's not a bounded function, and neither is cosine z. Yeah, so please see, this is not exactly what we do in R. In R, sine and cosines are always going to be bounded. Yes, here you see that we have proved that sine and cosine are not going to be bounded. Of course, it is bounded when y is 0. That's not a point. But generally speaking, for C to C function, this what sort of function is sine and cosine? These are entire functions. As an entire function, this is not a bounded function. Yes. Okay. I will write down some general formulas which you need. Formula. This you need to check. Yeah? So this is very simple. It's not very difficult. Cosine z1 plus minus z2 is, you can guess what is going to happen. Exactly the same thing. Cosine z1, cosine z2. This you can prove. Minus plus. So plus it is minus. For minus it is going to be plus. Sine z1, sine z2. Yeah. So this is exactly the real formula. Whatever we do here, also we do the exact same thing. And sine of z1 plus minus z2 is nothing but sine of z1 cosine of z2. Yeah, plus minus sine of z2 cosine of z1. Okay, cosine of z1. Okay. Also, this is true. Though they are not bounded, they are not bounded. Sine and cosine are not bounded. Okay, cosine is not bounded. So, but this is true. Cosine square z plus sine square z is always going to be 1. Yeah, you can check this. This is very simple. So you see, although they are not bounded, they are going to be the sum, that formula, that whole. So it's a weird situation, right? Some properties are very nicely followed. Some properties are extremely wild. Okay. So that is more or less sine and cosine. So now how many entire functions are there? You know, we know that the polynomial z squared, those sort of things are entire. And exponential functions, that we have defined, that's an entire function. And then you have cosines and sine, they are entire function. Okay. Now we'll prove something called a hyperbolic function. Hyperbolic functions. Okay. So basically we are actually building up our database of some basic functions. So now we'll define the complex hyperbolic sine and cosine. So basically we'll define complex hyperbolic z. Yeah. And from our real definition, we know that this should look like this: half e power z plus e power minus z, right? It should look like this. This is the definition. So we define this, and we define sine hyperbolic z to be half exponential z minus exponential minus z. Yeah, those are the two things, and this is actually motivated by real, right? Motivated by real. Clear? Okay, and you can actually show that this is true, right? That also similarly you can show that cosine hyperbolic z prime, this is going to be sine hyperbolic z and sine hyperbolic z prime is going to be cosine hyperbolic z. Yeah, so exactly the similar sort of thing which we know from our real thing, that holds here. We can also define tan hyperbolic z to be sine hyperbolic z by cosine hyperbolic z. Okay, and cot hyperbolic z to be cosine hyperbolic z by sine hyperbolic z. Okay, secant hyperbolic z is nothing but 1 by cosine hyperbolic z, and then cosec of hyperbolic z is nothing but 1 by sine hyperbolic z. Okay, so these are all hyperbolic functions. Yeah. Now the properties. First of all, do you think that hyperbolic functions are going to be bounded? They are never going to be bounded. Yeah. Are they so properties? Number one, they are entire function. Entire. Okay. Why entire? Exponential z is entire. Exponential minus z is entire. So if you sum those two up and divide it by half, that's going to be entire. So they are entire. What I mean is cosine and sine. Okay, right. Those two are entire functions, and then you have to check whether tan, cot, sec, cosec, those are entire or not. Of course, they are not, because you do realize that is a cosine. So basically, the denominator may not be defined everywhere. Yeah. So please keep that in mind. So sine and cosine, they are going to be entire functions. So hyperbolic, of course, cosine hyperbolic and sine hyperbolic, what I mean. Okay. And the second thing is that they are not bounded. Of course, they are not bounded. They are not bounded. How do you show that? So if you take y towards infinity, then you can see that e power z is going to be blowing up, and hence this is not going to be bounded. So please, you can check this part. Okay, and there is another property which is a very nice property, which actually binds this cosine with the hyperbolic function. So you can check that cosine hyperbolic iz, yeah, just put it in the formula and check. So please check this, is nothing but cosine of z. Very nice, right? And sine hyperbolic iz is nothing but I times sine of z. Yeah, I hope this is clear. So you can check this part. Please do that. So with this, I am going to finish this part. So essentially, we have three particular things. We have exponential, we have cosine, sine, and we have hyperbolic functions. All of these functions are going to be entire, of course, depending on the function. Cosine, sine, those are entire. So and cosine hyperbolic, sine hyperbolic, they are going to be entire. And of course, exponential is entire. So those are the entire functions. Derivative also we already knew. In the next video, we are going to talk about something which is very, very important and a little complicated than this. This is very simple, right? So which is called the logarithmic function. So thank you.